Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. We are going to be doing, I think today, I'd like to take a look at some lighting stuff that we mentioned. Let me see if I've got it here. I know we did some drawing. Alright, we put a little multi-res sampling in there yesterday, and we're going to have to look at that in a little more detail. But first, I think I might also address the stratified sampling stuff. Just to get everything in there, I'd like to get all three of these in there, probably before we start going down and turning the crank on any one individual thing. Because one of the problems is that they're kind of interrelated, right? I don't really know how to compartmentalize them very well, other than saying, you know, well, we know that each of these might be useful and might make a difference, and so I kind of want to have them in there as we start to play with any given one of them and try to improve the variance. I'd like to kind of know what we're dealing with here, right? So I'm going to take a look at the stratified sampling stuff today. And in order to take a look at the stratified sampling stuff, I think what we might want to do is put in a real random number generator, at least a reasonable one, and just maybe get a little bit of a feel for how that stuff is going. So, you know, I'm not a number theory guy, so I'm not really going to spend a lot of time talking to you about random number generators in any real depth because they're not my area of expertise. I tend to just go with the following method, which is that trust that some number theory people out there have done a good job making random number generators, but that I don't know who they are, and then create some kinds of tests that are representative of how I want to be using my random number generator, and verify which ones of the random number generators that they have created work well with the constraints that I want, right? So that's my typical approach to random number generation, is like saying, okay, look, I don't know how to make a good random number generator. It would take me some time to study to learn what I would need to know to really be any good at that, right? Lots of people have made random number generators, but I don't know which of them to trust. So what I can do is make tests that show me visually whether or not a random number generator is doing what I need, and select one that's the fastest one probably that satisfies that test. That's all I really need, right? And that's a nice luxury that we have in game development. That wouldn't fly in cryptographic security, for example, because there is nothing to visualize. In cryptography, whether something is breakable or not isn't necessarily visible to the eye. Now, obvious problems may be visible to the eye, but non-obvious problems that are still exploitable may not be. And so there's plenty of fields where you need to really know your number theory and have a really good idea about how these things work and be very up on the field in order to make a good decision about where you would get your entropy from, right? Game development isn't really one of them unless you're talking about securing the channel of a multiplayer game, let's say, in which case you're back to cryptography. But assuming you're talking about what we normally care about in terms of random number generation, which is visual effects, or gameplay distribution of things, right? What you can typically do is just create some test that shows the output from a typical run of the random number generator in the situation that you care about, and then you can usually evaluate it from that. And that's it, right? So in our case, for example, what we can do is we can look at what the distribution of rays shot by a random number generator is, and then we can look to see whether that distribution of rays is giving us some kind of an unfortunate clustering that we don't like. If that's the case, then we know that that random number generator isn't quite what we need, and we can use one that's more sophisticated or different. If we aren't seeing that, if it looks like the random number pattern is pretty stable and pretty consistent, then we really just don't have that problem. We don't need to consider it much further. So that's really my take on random number generation. That's how I typically view random number generation. And so what I would say about that is that's how we're going to approach it for this problem and probably any problem in Handmade Hero. And we're not going to dig any deeper into it than that because that's really not my field of expertise, and I wouldn't really have much to say, right? I'd just be like, I don't know. There's some numbers that come out of it, right? And that's not particularly valuable. All right. So the first thing we need to do here, regardless, and this has nothing to do with the random number generator, this is even just basic before we even get there. We're going to need a way to see what's going on. Because right now we have no idea, right? Right now, all we know is what we see on the screen. And what we see on the screen, right, oops, is as follows. Here we go. So here is our screen, and here is our lighting. And what we can see from the lighting is that we get a little bit of flicker. We would like to reduce that flicker, but we have no idea beyond that what's actually going on, right? I mean, as I move around this world, it looks like the lighting is working relatively well, and it looks like it's fairly accurate. So we don't have much reason to believe that, for example, our raycast is totally wrong. But on the other hand, we have no actual hard evidence that the raycast is really even doing a raycast. We don't know. We're not drawing anything. So what I'd like to start with, before we investigate that aspect of the program any further, is I would like to figure out some way to draw, say, for example, one of these squares, be able to pick one of the lighting points on it and say, let's look on any given frame, let's see what ray directions it is sampling, right? Just a basic visualization tool like that would be nice because it would let us know whether we're even sampling in a reasonable set of directions to begin with, right? I expect to see a nice sort of random shooting out of the hemisphere with no real correlation, just some random white noise there, right? So if we were to look down at, say, this one, I would just see like a bunch of random lines shooting out of it in all different directions, but we don't know that that's what we'd actually see. Maybe we'd see them all shooting one direction one frame and all shooting another direction on another frame, and that would give us some information that some of our flicker is actually coming from just really biased sampling that we could get rid of with stratified sampling or a better random number generator, blue noise, or blah, 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 right? So that's more what I want to look at today, is just like, let's get into some sort of a position where we can assess our sampling method at all, then take a look at whether the random numbers need to be improved, then take a look at whether stratified needs to happen in general, and then we can be a little bit more satisfied that our sampling direction is not part of our problem, which right now we don't know. It could very well be. All right. So if I remember correctly, at one point we did actually make a way to draw a line, I think. I don't actually know if that's true. I think a long time ago we did, though. So I'm going to take a look and see if that's true. So there is a line segment call. So in theory, it seems like we would be able to have some kind of a line drawn in the direction of sampling. So what I'd like to do here is sort of put this push line segment call into action, if possible, by loading up... Oop, I did not load up our project file. Here we go. By going in here and sort of trying to figure out a way to extract what directions were sampled from something and draw them. So in here, I'm just going to go ahead and say, all right, let's take the lighting code. And in here, we've got this output lighting points recurse function. What if we just said, okay, one of the things that we want to do in here where we do lighting points, in addition to doing this, we're also going to do something that outputs a bunch of directional sampling lines, right? So how would we do that? Well, in theory, we might even be able to do it in here somewhere inside compute light propagation. I don't know how smart of an idea that would be. But for example, what we could do is say, look, here in sample hemisphere, we get a bunch of these sample directions. What we could do in here is try to draw them, right? The reason I don't really like doing that is because we don't know whether we're set up in here for that, and we're introducing some extra code in here. So what I might do instead is say, look, let's put the code for drawing those out here somewhere, right? So if I'm going to do output lighting points recurse, right after that, I'm going to do something where I draw some of these line segments, okay? And what I'm going to do is I'm going to say, all right, there's a base P, right? So there's a base P here, and I don't care what the color is. Color can just be white for now. Doesn't matter. And we'll think about that in a second. What we want that to be. I don't know what the thickness should be. We'll tune that later when we see how thick it actually is. But then we just need a base P plus, you know, a sort of a draw length times a direction That's all we really need. We know we've got that white bitmap situation going on here because we don't really want to texture these guys at all. And we've got the render group. So if I want to, I can do like something here where I just have debug lines, right? So I can do U32 debug line index equals 0. Debug line index is less than however many we're going to do here. Debug lines, right? And I don't know, maybe I can even just put this in here. Debug line count, something like that. And then what I can do is I can just grab these debug lines out of the solution and just assume that they're getting stored, right? You know, what I could even do is make the color be something that can be recorded here as well so that we can record those debug line colors a little more specifically, right? So that's a pretty good way to push the debug drawing out of the part of the code that's actually doing work and let it get drawn later. So what I could do here is say, okay, let's suppose that we've got in this lighting solution just some information about these debug lines. So I can maybe just have in here a little struct called debug line. In there, I'll have you know, from P to P and a color. And you know, I don't know if I really want a thickness or not. I probably don't for now. That'll probably be hard coded. And then in here, yeah, I can just say, okay, I've got a debug line. It's going to be coming out of this array, like so. And I'll just let this tell me what to do. So I won't even do it that way. I'll do it like this, right? So then we're drawing these line segments at the end after we draw everything else, and off they go. So when I do this, I just need some way of storing these and pushing them on. So I can do debug lines and say that there's, you know, however many debug lines there are. I don't care. It can be some really high number. And then I can just have a debug line count in here. And we can just draw debug lines to our heart's content. All day long, it doesn't matter. So when we come through and we start our solution, we can just set the debug line count to 0. And then when we're doing anything else, we can just push things on there. Now, I don't want to push on all of the samples because that would be absurd. I need some way of targeting a particular sample point. So what I'm going to do here is just say like, oh, well, okay, if the sample point index, for now, you know, equals sample point 100, I don't know why I'm picking 100, but we'll want to set that later, let's say. Then we'll just go ahead and push these on here. So we'll just say push debug line, and we'll give it the lighting solution. And then I'll say, well, I know where I'm sampling from, right? And I know which direction I was going. And I can adjust the length here however I want. Right now, we'll do it a meter. Maybe we want it shorter than that. Maybe we want it longer than that. I don't know. Doesn't really matter. But I can push a debug line on here, and then I just need a color. For now, we can just set the color to be white. So that would be it, and it would draw a debug line for every ray that shot out of sample point 100, and that would be it, right? The other thing I could do is I could say if I hit a box, I'm going to set it to white. If I didn't hit a box, you know, I'm going to set it to something else. So maybe I could even do green and red. So, you know, let's say I do a green for a hit and a red for a miss. And then I can also get a little bit more information there by just setting the color to whether or not I thought I hit something. Another thing I could do is draw to actually the place where the ray hit. Now I think about it, that might be kind of nice, right? So if the ray didn't hit anything, I would draw one thing. If the ray did hit something, I would draw something else. And that seems kind of nice as well. So in here, I can recalculate ray P if I want to, right? So I can do here like endpoint equals that. And then I can say if hitbox endpoint equals that. And then I can sort of say, all right, well, we'll just draw out from the sample point some distance, right? If the rate, you know, it's the same equation. I could simplify this even more. In fact, it's really just this, right? Where did the code go just then? That was weird. All right, that was really strange. It's just this, right? I'm just saying if there was a hitbox, like if we actually hit something, then I want to go out to where the ray hit. Otherwise, I'm just going to use that draw length, that stand-in. Right? So, we take a look at this, and that's pretty reasonable. That'll draw a line to the point that we actually thought we found, right? Or the surface we thought we found. Otherwise, we aren't going to bother. We'll just draw some distance away, some short distance away, right? And maybe 1 meter is too much, so maybe like, a quarter meter or something. So it's a pretty short line if it didn't hit anything, right? Okay. So that will do that pushing for us, and all I need to do now is make an actual function that puts that on here. So in here, we'd say, okay, let's do a push debug line. That push debug line is going to have all the stuff that we just said. And what we'll do here is just say, well, there's a debug line. That is the solution debug lines plus debug line count plus plus. And again, we want to just do an assertion there that we're not overflowing the buffer. So we're just going to say, look, as long as we got room for this debug line, let's push one on. And then fill it out with exactly the information that we just got. And that's it. So that's all I wanted to do. Oops. And now, in theory, we can, as soon as we debug this, we would actually have something that's going to draw these little debug lines for us. Not in this mode, but in this mode, right? Oh my. I guess one thing I failed to account for is the fact that that point is going to move around. That's less useful. Well, yeah, we'll have to do a little something to fix that. Shouldn't be too hard, but I forgot about that. These points aren't coming in with any particular ID on them. So there's that. That thickness is way too thick. That is one thing that we should fix here. Those lines are just way too thick. Drop that down significantly. There we go. That's a little bit better. I might make that a tiny bit bigger. So that's more what we're looking for here. There we go. And I mean, ideally, I want to be able to do one close to here. So I think what I'll do is I'm going to do just a little bit of cheekiness here. I'm basically going to say, like, look, okay, let's do something that's like debug point index. And what we'll do is we'll say, instead of 100, I'm going to say whatever the debug point index is the one that we draw, right? So then when we start out, what I'll do is I'll just do a sweep where I do a test. And, we're going to go over these points anyway. And what I'll do is I'll just say, look, there's going to be like a closest point distance, or debug point distance. And that's going to be set to F32 max. And when I come through here, I'll just say, look, if this particular point, whatever point we're on, if point P, let's do this distance, we'll do a distance squared of the point, whatever point P is, and our debug point location, our debug location, which for now will just be 0, 0, 0. I'll just see, look, if we can find the point that's closest to the one to where we sort of want to pick points at, we'll just use that one, and that should be relatively stable. So I'll just take the closest one and go from there. Oops, this distance. So that, something like this, right? And that allows us to set an actual location. And then that location we can move anywhere we want, obviously, and it will hopefully always pick a stable point. So there you go, and that does seem to be working pretty well. Okay, so let's go ahead and increase the resolution here down to where we're at. That is shooting out the bottom. This is the bottom point here. Still might be a little too thick. Oops. Yeah, that's a little bit better. So I guess it depends on the distance we want to view them from, obviously, because these are not screen space lines. When I'm in the debug view, I kind of want to set my clipping plane to much closer so we can see things a little bit more easily. So I kind of wonder if, again, if that clipping plane also wants to be modified when we're in that mode. So in here where we do debug camera, you can see we set the near clip plane to 3 meters, right? Because it's very far out. That was kind of by design, right? But if we're in debug camera, I almost want to say set it to something much closer. So like, you know, normally we clip there. If I switch to a debug camera, I'd rather not have the clipping so I can get right in there and see what's going on. So now, right, when we view one of these things, I can really sort of zoom in and see it much more accurately. Yeah, if that makes sense. So what I'd like to do is move this up a little because I'd like one to be sort of in the region we actually care about here, not upside down. So what I'm going to do to get that is I'm just going to go and take debug location. And I'm just going to move it up a little bit to, I don't know where it should be exactly, but I'm going to try and get something that'll be on the upside. So here you go, right? And one of the things that you can see about this, so, you know, if we just take a look at this in context here, and I'm gonna basically avoid doing any work here. I'm gonna set us into debug mode so that the frame rate will be super slow, so I can look at this a little bit more cleanly rather than adding a pause feature. Oh well, you know what? No, I'm dumb. Why would you do that? Don't do that. That's stupid. All I really have to do is this. So, when we're in this world mode here, we know whether or not, inside the lighting solution, we can just have a thing that's like update debug lines. So what I can do is just say like the debug lines get updated when the debug lines get updated, and that's just how that works. I could even make it so that this output lighting points always happens. I don't know how well I can really do that. Let me see if I can. So let's just see if inside here, inside lighting test, I don't know if I can actually make these calls here if everything's set up properly for it. I'm going to see whether I can. Yeah, so I would have to, well, you know what? I could still do that though. Where is that? Here it is. So it looks like I can do that just fine. And so that's kind of nice because now I can have these going at any time, right? And then what I can do is just make it so that whether or not they're updated is actually predicated on, excuse me, on whether or not we're sort of saying that we should update them, right? So what I can do is say, all right, if solution update debug lines is active, then we clear. Otherwise, we don't. And inside push, we do it as well. So now when we run, nothing will happen, right? We won't draw any lines because that flag isn't set to true. And then what I can do is inside world mode here, I can add a key that will swap that in and out, right? So what I can do is just say, like, okay, you know, if the F2 key is pressed, then the test lighting update debug lines just gets toggled. So now I can do that, and you can see that when I freeze it, we can see exactly where those lines got shot. And who they got shot to. You know what I'm saying? And one nice thing about this, again, is we can sort of validate whether or not our raycasting is working correctly or not. And so what you can see here especially is you can see one of the artifacts of our multi-resolution stuff. So do you see where this ray ended here? It didn't actually hit anything, right? And so what happened there, and this is maybe something, again, that we want to look at. This is why visualization is very good, because we don't actually know if it... let me see here if I can do it. It's hitting this, right? And exiting out early, right? Because we said that if it went that far, it could. That was something we said, right? So anyway, looking at these debug lines here, I would also say that it's kind of odd. I would say that looking at these debug lines, I think I also can see some reasons why our spatial partition needs to be improved for multi-res. So one of the problems is because of the way that we're doing the splitting, we end up with not very good spatial distributions, right? Like these things here, you almost want more of like an octree, where you're gonna fill the entire space whether the bounds of that thing enclose it or not. Because for the purposes of early outing your raycasting, you want to hit the thing that's over here, sort of. Probably. I don't know. Maybe you don't. It's hard to say. Might be fine. We'll see. Anyway, ignoring that for now, because that's not really what we're talking about here. One thing you can see just by looking at this directly is that stratified sampling probably would help our flicker quite a bit. You can see, like, sometimes it's looking over here, sometimes it's not looking over there at all, sometimes it's looking over there, sometimes it's not looking over there at all. So for 16 rays, spreading them out more evenly is probably a pretty good idea, right? Just in terms of how much flicker we're probably getting from this very different set of distributions, I think would be good. It doesn't look to me like the random number generator is all that bad. I mean, we haven't really tested it yet, so it might still be... Again, it's not a random generator right now, it's actually a table. But it doesn't look like it's doing anything particularly stupid. It looks fairly white noisy, actually, so I don't know that we're going to improve that all that much. We might, but I don't know that we're going to improve it all that much. So the important thing here, I think, is to go with maybe the stratified sampling a little bit more. And try to guarantee that we have a little more coherence as to where we're shooting these rays and see if that helps our flicker a little bit. So how might we do that? Let's take a look. Now in this case, we're just trying to get a picture of the lighting environment that's around us. We don't really have a reflectance function that we're worried about, and so that's going to inform the design of this a little bit. The reason it informs the design of this a little bit is because if we did have a specific reflection function that we cared about, our stratified sampling would want to take that into account, right? Because if we know that we very heavily reflect light from a particular set of directions and don't really reflect light much from others, we probably shouldn't bother looking as much in the area that we don't reflect light from, because those samples, even if they come back with light, aren't really going to contribute to our overall look very much, and so concentrating samples there would typically be a bad idea. In this case, we don't really have that. The only thing we have is a cosine fall-off, and so to a certain extent, the only thing we really know is that things that are up here tend to contribute more than things that are down out here, right? So it does mean that we probably want to take a look at like this outbound cone here and maybe sample this more heavily than the sine cone here, for example, something like that, right? That's just a, kind of a vague notion. So how might we sample this? Well, if we imagine looking down from the top here, and we sort of have the idea that, well, there's sort of, rough directions we might sample out, right? Looking down from the top, one of the things that we kind of want to do is we want to sort of look out in all directions a little bit, right? So we probably want to ensure that we're going to look, out into the world in some way that sort of resembles this. Right? We want to ensure that we shoot one ray kind of this way, one ray kind of that way, right? We sort of want to make sure that we're shooting rays kind of out in those directions. And then in terms of the elevation of those rays, we probably want to make sure that we have some distribution across the elevation as well. How exactly we want to do that is not immediately clear. We'll have to sort of play around with that a little bit, but it's, it's something like this. Okay. So there's a lot of ways we could imagine doing this, but I think the way that I would probably say we should do it is with sort of a bit of a maybe templating scheme to a certain extent. Like, I might say maybe what we can do here is have some notion of the hemisphere where we've pre-computed some of these, and then maybe we just blend between them, right? In order to, at certain ratios, in order to get what we want, right? I'm going to have to think about exactly how I want to do this. So, similarly, if you imagine looking at the thing this way, sort of as we said, like stuff that's really coming in at a steep angle there is not as useful. So we'd also like to sort of be shooting out more that way, more biased towards upwards. And we'd like to make sure we shoot some in the upwards direction. So we've got kind of a lot of competing concerns here. It's a little bit difficult. It's pretty easy to make sure that we shoot some in the upwards direction, right? Because you can imagine just taking the surface normal of whatever this point is, right? And basing some randomness off of that surface normal. So we could pretty easily shoot in sort of a square around that, right? Or a cone, and make sure that we generate like at least 4 points in that direction always, right? So we could always guarantee that we get some facing upward. And so then the question is just how do we make the ones that are facing into the sideways? And one way to do it, again, might be to take those, maybe do the exact same thing. Maybe we just have like a series of sort of these vectors, and we're going to go ahead and construct the randomness off of that. I am curious. I don't even remember what we're doing right now. So what we're doing right now is we just say, all right, generate something in the sphere, and then if it happens to be pointing the wrong way, just flip it, right? So that's, yeah, that's pretty basic, right? One of the problems that we have here is our lighting points don't remember their basis coordinates, so we don't actually, while we know the normal, we don't know the x and y axes. And that's probably something we need to actually keep if we're going to be constructing regular sampling based on that. So that's a little bit of a tricky situation, because it means we'd have to store a lot more information on our lighting. We have this information in the box itself, and so the question is, yeah, do we really want to bloat this lighting point out to the point where it stores all that, you know? And I don't know. But so if we had an x axis and a y-axis here, for example, we would be able to store that here inside lighting test. When we come through and we write out the normal, we can also write out the x and y-axis because they're actually known just based on the surface, right? The surface knows that information. Right, you can, this call right here generates it for the box. So we can, if we want to, just store a surface x-axis and surface y-axis, and we know the normal points out from that, so that would pretty much be it. Again, it just costs a lot more to like romp that information in there, but that's what we would need. So then when we go to sample hemisphere, sample hemisphere is going to be a little bit different now. So sample hemisphere would need like so. And now it has all of the information that it needs in to do constructions of that nature, but it still doesn't have quite all the information it needs to do everything it's going to need to do, and I'll explain why in a second. So this won't make any change, right? If we run this now, we would see the exact same sampling pattern that we saw before, in theory anyway. So that's fine. So the problem that we're going to get now is like if we take a look at what's going on here, we need to figure out a way to tell it what kind of sampling we actually wanted here. So we're going to have to pass a sample index so it knows what strata it's using, right? All right. So let's suppose, yeah, like I said, let's suppose we were going to do something along these lines. Let's suppose we did the simplest possible thing first, which is to say we just went, okay, look, if the sample index is less than 8 or greater than 8, let's suppose we split it up into two halves. One half samples upwards, one half samples outwards, right? And that's all we're going to do at the moment. That's it, right? So what we could do here, we can actually do this relatively easily, I think, because since we have the complete x, y, and n, which is effectively the z-axis, since we have the complete axis system, we can construct sort of arbitrary things here. So let's suppose we did something kind of completely ridiculous at first, just so we can verify it's actually working. What I could do is say, all right, you know, we're going to produce a result here. And in one case, what I'm going to do, if the sample index is greater than 8, I'm going to sample out the sides of this thing, right? So what I'm going to do is I'm going to take and do a normalize, but I'm going to do it a little bit differently than we were doing it before. I'm going to take a random bilateral times the x-axis, a random bilateral times the y-axis, so you can be anywhere in the plane. But the z-axis which is the normal, right? The z-axis, I'm actually going to say you only go up halfway, right? Now, on the other hand, in this one, I'm going to do the opposite. I'm going to say you can pick anything you want, but you're going to have to pick a z that's over halfway, always. And I want these to be less than halfway, right? Does that make sense? So I'm basically saying I'm breaking this up. And again, I'm not suggesting this is good at all. I'm just showing an example of how we can break this up. Don't ask me. What I thought I was doing there. Okay. So now, when I run it, and do my my sampling, I'm hoping to sort of get a little bit more. Oh wait. All right. I'll be honest, that's not at all what I expected. I must have messed something up. Well, actually, no. Maybe that is sort of roughly what I expected. Kind of chaotic out the sides. I was expecting a little bit more sort of distribution there. Let me just make this more pronounced to make sure I'm actually doing what I think I'm going to do. So these should be really flat out to the sides. Right? So now you can kind of see that, right? Do you see how we've got these ones that are shooting flat out to the sides and these ones that are shooting up? I'm going to stop updating debug and just count, right? So if you see how many are coming up here, 1, 2, 3, 4, 5, 6, 7. If I can quite count 8 there. 1, 2, 3. Should be 8. Can't quite tell if there are. They're all kind of quite close to each other. 1, 2, 3, 6, 7, 8. Yes, there are. And now there should be 8 around the ring. 1, 2, 3, 4, 5, 6, 7, 8. Yep. So you can see that is working, so I'm not nuts. And you can kind of see what I mean, right? So now we've got some that are pointing upward and some that are pointing outward, right? And they're not the same. Now, as I move around, you can actually see that it did change the character of the lighting quite a bit, in fact. Because we're biasing our sampling upwards now, you get people who have lights directly above them finding that light much more intensely, right? Because it's always going to make sure that it finds that light shooting a lot of stuff up in that direction. However, sideways lighting maybe not so good because now you've only got 8 and they're shooting way out to the side where they can't really have much of a contribution, right? So it really does change the character of the lighting to bias the sampling, even though the sampling is still random and possibly still covering most of the thing. It's not really, though, because there's probably a bit in there that's not covering. You can see that it does make a bit of a difference. So it's not, it is relevant how you choose to partition the space. Okay, but this is not really what we want to do. We want to do something that's going to give us a fairly even hemisphere covering on every frame. So the question is, how are we going to break up the hemisphere into pieces that will work well like that? And so, like I said, one way I think to do this would be to do a hemisphere table that kind of lets us pick a base vector that we've sort of pre-distributed around the hemisphere and sample off of that. The way I'm going to do that first is I'm just going to do none of this. Instead, what I'm going to do is I'm going to say, all right, when we sample the hemisphere, what I'm going to do here is I'm going to take a table that we have, and I'm going to use the sample index, and I'm going to AND the sample index. So the sample index I want to wrap. So if you sample more than is in the table, you just go back to the beginning of the table. So what I want to do here is the sample index, I'm going to and it against the array count of the sample table. So however many samples there are in the table, right? What I want to do here is say, however many samples are in the table, I want to take the mask that would tell you how many there were, and I'm going to mask it off. Now this only works if it's a power of 2, right? Because subtracting 1 from something only generates the mask if it's a power of 2. Because if it's a power of 2, then in bits it looks like 1, 0, 0, 0, 0, 0 something. Yeah, so it's just some set of zeros, right? So if you subtract 1 from it, you lose that initial 1 and get 1s everywhere else, and that's the mask that keeps the thing anding properly, right? That keeps the thing within range. So very simple bit operation with a constant there to make sure that we always wrap. And then I'm just going to say this has to be a power of 2. Excuse me. So, all I'm going to do at first is just sample the sample table. And that way we can see what the sample table is. We're not going to inject any randomness into it. Now this is a very bad idea for lighting quality because it means it will just find an exact, as you move around, as it'll just like immediately like have discontinuous lighting as we move around. But it will allow us to see whether our sample table looks right, if that makes sense. So what I can do here is just say, all right, let's build the sample table. Now we only have to do this at the beginning of the game, but I'm going to do it every frame anyway because it's going to be pretty cheap to build this table. Where are we here? Nope. There we go. So what I'm going to do here is just build the table. So sample table. What we want to do is kind of build this table up. And we need to come up with a way to sort of distribute these points. Now, maybe we don't, I don't know that we really want it to be 16 long, and maybe that we want to do 18 long and sample twice from every one of them, for example. I'm sorry, just 8 long and sample twice from each one of them. That's hard to say. I'm not sure. So we'll have to play around with that and see how big we actually want the table to be. And that's how many sort of buckets of the hemisphere we want, because we can choose to have 16 buckets on the hemisphere and sample them all once for 16 rays, or we can have 8 buckets on the hemisphere and sample them all twice for 16 rays, right? So it's kind of up to us how we want to do that. That's just, you know, depends on what we find to be more effective. So if we take a look at the sample table here, I'm going to go ahead and set, first of all, I want obviously one that's directly up. I think that's a pretty important thing to do, sample around the direct up vector. I'd like to sample ones that are close to directly up. So I also probably want to do something that's like 4 quadrants around there. I'm not sure exactly how I want to do that, but you know, we can play with this a little bit. So this is just going to be me sort of randomly distributing these. So I have one up and then like, you know, 4 quadrants around that one up. Then we kind of maybe move down to maybe the 8 wide ring all the way around. And I'm not sure exactly how we want to do that, but again, so let's just say we did something like this. Two, 3, 4, 5, 6, 7, 8. So something like this, where we said, all right, let's do every permutation of these. So I should do this more systemically. So we do So, okay, we've got -5, -5, -5, 0, -5, 5. So that's all the ones on the bottom. Then we would have those 6 there, and then we also would need the ones that have 0 on them. So we just need -5, 5, -5, 0, -5, +5, 5, -5, 5, 0, 5, 5, and I guess we're missing 1 here. Oh, no, because we don't need 0, 0. So then in here, oops, we just have 0, -5. So that's it. That's all of them. And then for 13, 14, and 15, those are just random samples around the edge, like low ones. We don't really have quite enough there for that. So I don't know, maybe the answer is there should be something here a little bit more rigorous. I'm not sure. Let's say this is just something like that. And we'd be missing 1 here, is I guess what I'm saying. Because we really want 1 more. So what we could do is just say, all right, maybe it's more like this. And then we do get that last corner sample. So that's a sample table, right? And it's all good. And in theory now we should be able to see a very regular sampling pattern. So it should be no flicker at all, right? Because it's always sampling exactly the same stuff. And that is true, right? There's no flicker. But it's not sampling the lighting very well because it just only happens in those specific directions, right? Okay, so here are those directions. I'll be honest, that doesn't look quite right to me, does it? Well, no, actually it does. That's okay. Yeah, that looks pretty good. I think what I'm seeing here is these should be a little bit lower than they are, but other than that, I think we're pretty good. So those mid-range octant ones maybe need to be flattened down a little bit. So, you know, maybe these need to be more like this. Right? And that looks a lot better to me. And as you can see, the lighting still works just fine. It maybe just isn't quite so accurate in a lot of cases, and it has some weird, like, kind of jerks on and off, right? Because it never has any soft smoothing around those edges. But it gets rid of that, and it misses some obvious lighting things, right? But again, you can see that it gets rid of the flicker because it doesn't change per frame. It's only when something moves. So that's exactly what we're trying to mix in here, is the fact that a stable sampling pattern wouldn't flicker, but it misses information. So we're trying to combine the two together to like get the information over several frames if we can, but reduce that flicker by keeping the samples stratified in a similar way. Okay, so let's suppose we added a little bit of noise in there now to sample Hemisphere, right? We come up with one of these, and maybe, you know, let's say all we do is we just perturb around them a little bit, right? Because we certainly could. In fact, we'll still leave this in here. Actually, I don't know if we even really need to do that. But let's see here. So if we take random bilateral, so let's suppose we just do pretty small perturbations for now. And you know what? Let me do it this way. Oh, ah. So let's suppose we just said, okay, you know, we're just going to do a small perturbation for now, maybe a quarter at most. And our result's just going to be whatever the base vector is perturbed by that much, right? And let's see what kind of sampling that gives us, just as a start, right? Not saying that's particularly good, but, you know, there we go. So it seems like that's maybe still a little bit too much movement. Let me see here. Calm that down a little. So there we go. That's maybe a little bit more gentle, right? Unfortunately, there you can still see we're not really covering everywhere, probably. You can see these two things don't quite get together. Let's expand that out a little bit. Now they're much more able to sort of converge there. So you can see we still get a lot of apparent flicker there, right? In terms of how much noise there are, you can sort of see it. I'm going to go ahead and see what the threshold is there. So if I set the ratio to 0, so we're just using completely stable bases. So now we get no flicker, right? Let's suppose I set it up to put in a little bit. So you can pretty much see, you know, the flicker appears very quickly. You know, very little perturbation of the sampling directions already yields pretty reasonable flicker there, right? I mean, it's not horrible, but it's definitely there. So let's say we put in a lot. But it is definitely, the reduction is noticeable. Like, you definitely do get significantly less flicker as you bring that number down. I also forget how many frames of smoothing we're doing right now. Let's take a look at that number. I don't know where our T update is. There it is. So right now we're doing 20 frames. Right? Looks like a smoothing. So 20 frames is, at 60 frames a second, is like a third of a second of lag in the lighting, right? So we could do more like, if we wanted to, we could bump that up a little bit. I'm curious to know like what the happy medium is there as well. Oh, I forgot about that little thing where you can look over ledges. So I'm not sure how I feel about that. I mean, another strategy I could try here, which sounds kind of nuts when I say it, but actually maybe makes some sense, is if we didn't use randomized sampling, so we actually use 100% predictable sampling, and just did the samples over the number of frames we smooth. So let's say we say there's 10 frames of smoothing, that's 160 raycasts, and we just raycast them completely deterministically over those frames. Kind of a weird way to look at it, but I mean, in theory, it would work. So just like to give you an example of what I mean by that, you know, let's suppose I said, okay, look, here's how this is going to go down. Instead of having a random series that's stuffed in here, we're not going to do that anymore. Instead, what we're going to do is we're going to say, look, we've got a sort of a ticker, right? We've got like a little like I don't know, a counter of some kind, a entropy counter. So when you come through here, we're going to have an entropy counter, and we're going to say, all right, at the end, the entropy counter, we add to that. And if the entropy counter is greater or equal to the frame, entropy frame count, then it's equal to 0 again. So it just counts around there. Okay. And so then what we say is something completely ridiculous, which is like, all right, so then we say, well, our t update value is just 1 over whatever that frame count is. So we need it to blend over this many frames. So that entropy frame count is going to tell us what that t update value is. Our entropy frame count is just however many we want to blend over, right? So I don't know, 10 or 20, something like that, right? Let's say 20 because that's what it was, right? Then what we do is when we go to seed the series, we don't store the series anymore, right? Series does not get stored. So in here, instead what we do is we say, okay, we're never going to store the series. The series just gets seeded off of the entropy for this particular frame. So we say, okay, the series is just seeded, because I think this is how the series works anyway. I don't remember how we did this. Here, do we have a seed function? There we go. So we just say, look, you're going to random seed off of the solution's entropy counter. And that entropy counter is just, you know, some nonsense. Who knows what's going on here, that produces some value, randomly stepping value, produces some value off of this series, right? That's it. That's all it does. And so this way we know that we wrap every n frames and sample the same stuff again, right? Does that make sense? So this way we know that our entropy is not completely random. It actually cycles. So if we were now to look, we should see this looking the same. It should be like a repetitive pattern. Although honestly, it doesn't look like a repetitive pattern to me at all. So maybe that ain't right. Oh, Yeah, so I guess the problem there is every individual point is still going to be in a different order. So this would have to be per point that we do that, actually. So I take that back. This actually has to look, since we're going to do the random sample here, how often does this series get used? Just there, right? Yeah. So this actually has to be like that. Sorry, like that. And we probably would want to randomize it based on some properties of the point as well. But sorry, so this is actually the stable version. And so now it should look like a repetitive pattern, I think. Yes, and now it does look like a repetitive pattern. Okay, so now in theory, it's only picking up, over the frames where it's doing the blend. Now, at least in theory, it's going to be picking up the same results every 20 frames, right? So it's kind of an integration over those frames. The problem is we're not really doing a fair average over those in any particular way. Like, we're not doing something which allows us to really utilize all those samples because we're just kind of blending towards whatever the latest value is, and that's not necessarily what we would want. So the question is, can we do a little bit better than that by maybe making this be more of a moving average that would stably come out? I'm not sure if we can do that directly, but like here's an example of how we would try. So if we take a look at how we're doing our lerping right now, you can see us doing this here. If instead of doing it that way, we know that t update is basically the averaging amount. So if instead what we did is just accumulated trying to think of like how I could make this into a stable moving average. This is basically like one of those IIR filter kind of problems. Yeah, I'm not really sure. I'm not really sure we can do much better than that. Hard to say. Here's what I will say. So if we made the period about half, so, we updated, I guess I want the other way around. So the t update amount is going to be about, half of whatever the entropy frame count is. So we'll update more slowly than the number of samples that we take. I'm curious to know if that if that's something that gives us good results. Of course, I need to probably change this to be more like that, to be a fair comparison. So I'm not sure how much that really helps us, though. I'm also kind of curious. So there's just so many factors here. I'm having trouble. I guess I probably need to like start concentrating on particular ones of them. The other thing I was wondering is how much of that is from the average direction to light and how much isn't. So I'm curious, like if we were to say, hey, yeah, the solution average direction. Oh, so we're still doing that. So this is strictly color channel variance, right? This is what it would look like if we actually used the directional component as well. Which honestly doesn't really look much different. In fact, it looks a little different in terms of the lighting solution, but the flicker actually doesn't seem to change at all. Like, it doesn't seem to be an appreciable source of variance for whatever reason. So yeah, so I'm not sure. I feel like I'm missing something here, because I feel like these should not all be as similar as they are. And the fact that they're not is a little confusing to me. I wonder if our blending is still not quite what it should be. So here's... I wanna check a few things here. So for starters, I'm gonna try doing a little experiment here. I'm gonna do an entropy frame count of 10, but a T update of 1. So I just want to see what happens if we just use, if we just use the whole lighting solution every time. Because I want to see how noisy that is, right? And that's like incredibly noisy. So take the smoothing out of the equation. See how this is doing here. And, you know, I mean, I guess I can understand why. You know, because if you look at what's happening here, like let's suppose I move, you know, I take a look at how the, like this one frame that we're drawing here, for example. I mean, this one point that we're drawing here. If I move this cube in the way so that occasionally it hits it, right? Then exactly what I expect to happen sort of happens, which is that on a frame, when it does hit the cube, when it finds this cube, it'll be bright, and on a frame when it doesn't, it'll be darker, right? It'll go bright, dark, right? And that's exactly what you would expect from the random sampling. So that's like unsurprising. And so the ability for those really bright lights to sort of have that effect on everything, I guess, is, you know, it's kind of a... It's kind of an unfortunate aspect of that. But, so let me go ahead and play with this a little bit here. So I want to look at the entropy frame count. So let's suppose the entropy frame count was 1. This pattern should become perfectly stable, right? And it does. So you can kind of see that that gets rid of all of the flicker, right? But it means that a lot of light just never picks up the fact that there was a light near it, right? Which is unfortunate. And again, you know, that can be solved, certainly. And in fact, we could even say, well, you know, maybe the entropy frame count is a very small number. Maybe we only sample like 4 entropy frames, right? And then if the smoothing was over a much longer period of time, maybe that's sufficient, right? So maybe if the T update is back to 20 frames, but the entropy count, frame count is only 4, then the amount of variance you can get in there is pretty low, right? And you can see from that, right, that there isn't a lot of flicker by comparison, I guess. Although you still get a little bit, you know, in and out there. The other thing I could do, I suppose, is say, well, I could actually track all 4, like always track all 4 samples. Yeah, it's tough to say. Really tough to say. I'm going to try increasing this a little bit. I want to see what happens when this gets larger. So here we are running with a lot more. Of course, I guess one problem is it's hard to see what the flicker is when you end up tanking the frame rate. So I don't know if we have to like optimize more, I suppose, at that point. This is also a good way to look at our sampling pattern, right? So you can see how it doesn't have enough coverage. You can see like where the gaps are, if that makes sense. So if you take a look at what this ratio has to be, it's more like that to get like, you know, an even coverage. So anyway, I guess I'm not 100% sure on which way we should proceed at this point. We have a pretty good understanding about what's going on, but what we don't know is how much better we should get at taking and using samples before we just go, well, now is the time to just try to do the optimized version of this so we can cast more rays per sample point, right? Because at some point, casting the more rays per sample point gives us smoother values, and maybe, you know, at that point we're good enough. We don't really know. So that's a tough call, and I don't really know how to make it. Decisions. So at the moment, I don't think there's anything about our update that couldn't be partitioned. So if you take a look at compute light propagation, for example, I did nothing in here. It all just writes to the output array based on the sample point index. So in theory, we could multi-thread this pretty trivially. So maybe we should. And then we just have 8 times more array counts here for free. Well, maybe not 8, at least 4. So we could go to 64 arrays pretty trivially. So maybe we just should, you know? Right, so maybe I should just do something where I say like, all right, look, we want a work queue callback that's like, do lighting work, and then we've just got a lighting work pointer, and off it goes. So then in here we just say, I'm just going to do it like this. So I'm just going to say, all right, we've got a first and a stride. Actually, no, we don't. We'll just do a first and a last. So I'll just do that. And I think that's all we would need to do if we wanted to just get it going significantly faster so we can play around with it. So we could just make some of these and off we go. It would be exactly what you would expect. So yeah. So I'm not actually sure. Software render commands. I'm not sure exactly where we're supposed to get that particular piece of information. Because we've kind of got these two queues here, I think we can just use the game memory. We just want the high priority queue, right? But I don't know exactly where we get that. So I'll just do this first and assume we pass that in. So inside Handmade, we have that information inside game update. So this right here is where that queue comes from. I suppose world mode uses it too, right? It was doing it here. But I don't, again, know where the transient state information comes from, right? That would have to get passed in. But I suppose that's fine because actually when you call the lighting update function, so when you call lighting test, we could just have you pass it in, right? So that's actually fine. That's pretty straightforward. I don't mind that at all. So yeah, so this is pretty straightforward. I think all you do is this. So you just say, all right, compute light propagation, and it would say, I want to add a bunch of these entries in here. I'm not sure I remember if we say for the work queue what its distribution fan out is necessarily. But I suppose we can just chunk these up into however much we really want to. So we can just say like points per work, and points per work is going to be, well, actually, I guess we just want to distribute this among some number of things, actually. So even easier than that, I can just say lighting work, however many there's going to be, 32 of these or something. Probably even less. And then I can just say like, all right, the number of points per work is just going to be however many points we have, divided by however many works there are, and we also probably want to round up, right? So that's how many points per work there are. Then we would just go like work index equals 0, work index is less than however many we have, and then each one of these gets filled out in series. So lighting work equals works, oops, work index, and then we just add each of these on there. So we say like, okay, add to the lighting queue the do lighting work function, and here's the work. So then the work just needs to know the solution, the first sample point index, and the one past last sample point index. So each of these is going to be like, okay, the first sample point index is going to be 1 plus the work index times points per work. And this is just going to be that, and then that's it. Right? Pretty sure. And off it goes. So I'm pretty sure that's all you need to do. And I don't know how well that'll work, but I think that's it, right? Or at least it should be. So let's take a look here. So there's compute light propagation. It does get called 16 times, so that's good. And where is... So let's see if we can make it any faster here. Well, it didn't seem like that went faster, and it should, right? Unless we're completely memory bound, which I doubt. So if we want to do this single-threaded, we just do this. right? Something is up. What did I do that made this so slow all of a sudden? Because we're just still doing 16 rays. This should have been exactly the same, right? There should be no difference between those now. What did I do? I've done something horribly wrong. I just don't know what it is. So if I pass those exact values, and in here, just curious. If in here I say, okay, this is 1, this is point count. Nah, it's still slow. So why did that magically get slower? We're only calling compute light propagation one time. And I thought we were significantly faster than that when we were only doing 16 rays. Maybe I'm missing something here. I mean, it could be that this slowed us down. I guess I don't really know. This is what we had before. Oops. Yeah, that has nothing to do with it. So I'm not sure where did we suddenly take a speed hit there for something unrelated to what I was doing, apparently. Unless I missed something that we did earlier that caused that change. I'm not sure what would have done that. Where is... look at our stats here. I guess it's because this world is larger, I suppose that is where we're getting that speed drop from. I guess that's true. So before, when we were running quickly, I suppose we were running on the smaller world. Either way, let's just go ahead and say, if we distribute this work, we would expect it to go faster, but it did not go faster, right? Oh, I guess it goes a little bit faster, but not particularly much. I also don't know, so on the queues, how many of these do we have? So I guess one problem with this is these are not tuned to the number of CPUs we have either, which I suppose isn't particularly great. We never actually did a get CPU call here, it looks like, for whatever reason. So I'm not sure what's up with that. If we take a look here for the... Oops. There we go. If we take a look at the CPU utilization here, I'd also be interested to see what that looks like when this runs. So it does use the CPUs quite handily here. But for whatever reason, it does not get particularly much faster. What if I split this into less? Just curious. Strange enough, that's worse. This is peculiar. Actually, let's split it into more. No real change once you get up over a certain amount. Yeah, that is pretty bizarre. Let's see how resilient it is to changes in this. So let's say we crank this up to 64. Let's see what the difference in speed is there. So with multithreading on, it's about 170. So you get a minor speed up, I guess I'd say. So from multi-threading that on the CPU side, you get a pretty minor speed up. The speed up is, you know, about 25% of the total time you save back, maybe a little less. So it's pretty minor for going from a single thread to many threads. That's kind of peculiar. It's possible that if memory bandwidth is entirely to blame here, then that could be, but that doesn't seem super likely, like that would really be the case. So I'm a little bit surprised to see that that's happening. Now, granted, we haven't looked at this hardly at all, so it's kind of hard to make any sort of judgments about that, certainly. So I wouldn't suggest that there's anything... you know, it could be some fairly straightforward stuff is happening here, and we should just take a little bit of a closer look at it. But at the same time, it's just it seems like that should have gotten faster if you multi-threaded it naively, and so I'm not sure why we weren't seeing that. That suggests that maybe something weird is going on, and I'm kind of curious to find out what it is. I would like to look really quickly. I'm just going to take a quick gander here. Sorry, this won't take too long. I just want to take a look inside this routine to see what's going on. You know what else I would like to do, actually, now I think about it? I'd like to time the overall as well. I just want to be able to see what's going on there. So it's entirely in compute light propagation. And there are a couple things in here, so I guess now I think about it, there's a couple things in here that are problematic. So we are doing a statistics gather, which is bad. Right? Nope, that's not what I'm talking about. So like this, for example, is really bad because that cache line is going to bounce around. So I'm going to just take these out for a second. Just anywhere that I was changing a value in the solution itself, I just want to get rid of that. All right, so I don't think that was probably enough, but I just want to see. So wait a second. Am I still casting all the rate? Yeah, okay, so that was it. Right? It's kind of nuts, but if you look at what was happening there, the fact that we were adding a number to a shared cache line that whole time was enough to drop our frame. I mean, let's just verify that that's the case. So there's one put back in. There's the other two put back in. I mean, look at how fascinating that is, right? All I have to do is add one plus plus. I think it's just one of these. This is it, right? If you just get rid of this one plus plus that happens to either of those two, you get rid of that, and your frame rate triples. More than triples. Ladies and gentlemen, multi-threaded coding. So, right, just the fact that we were operating on a shared variable there meant all of our threads were just locking up on that plus plus, I guess. Right, waiting for that cache line to bounce back between the processors, which is real bad. And just that was enough to totally thwart the speed improvement. Pretty cool, huh? So yeah, so if we wanted to keep those statistics, we still could. We just want to add them into a frame-based thing instead of into the solution and then add them at the end. But that's pretty fascinating, right? It's pretty nuts how stuff like that works. So yeah, I mean, obviously we've got other stuff like that could be in play as well. The lighting points themselves probably want to be strited out so we don't get like overlapping there of cache lines either. So that part is a little nasty, and we should probably try and fix it. But that's kind of awesome and also kind of nuts. So here's the version running with 64 samples per point. And it's definitely quite a bit nicer. It's also running non-stratified right now, I think. Is that right? Or is it running stratified? Looks like it's running stratified. Yeah. So it may be that we really don't have to worry about the variance too much beyond where we're at right now, because a properly optimized version is going to cast enough rays to keep this going. And then we just kind of have global illumination, right? Which is kind of cool. So yeah, so I don't really know what to make of that, other than to say, wow, that's really cool. That if you aren't careful with your cache line ping ponging, you're going to be in a lot of trouble. We kind of already knew that, but it's just nice to see such an obvious display of it at work there. I'm going to go ahead, and I also just want to see like, if we sort of set the work point to a certain value and use that instead of the work amount, I'm just curious here. So if we take a look at the things that we're modifying, we know that we would want there to be, so if there were 32, I'm sorry, if there are 4 bytes per float and we're modifying 3 of them at a time for a color, that's 12 of those. So the problem there is those are not going to align very well on a cache boundary. Kind of nasty. So we would need to be like sort of on 2 cache line boundaries, because cache line is about you know 64 bytes long, and so 64 and 12 12 has a factor of 3 in it. So I think we would need to do 3 cache lines long, or 192, right? And 12 goes into that 16 times, so you'd want to do 16 points per, if that makes sense. You'd really want to be some multiple of 16 points away pretty much all the time, and to keep yourself from overlapping a little bit there. So I don't know exactly how you'd want to guarantee that, but let's say you wanted to do 16 points per work times some multiple. So, you know, let's say we want to do 256 points per or something like that. And then we would just do something like this where we'd have a lot of them. And here we would just do the loop a little bit differently. So we'd say something like first point index, you know, equals 0. First point index is less than solution point count. And then first point index plus equals points per work. Assert index. Actually, I guess I could still use the work index here. I suppose I could do that and just break out of the loop once we're done. So I could say work index is less than array count works plus work index. I could still do that. And points per work equals 256. And so what I could say is there, all right, look, let's go through here, get the work out, do it exactly where we're doing it, and when we run over, that's when we know that we're done, right, in a sense. I still need to be able to add it to the queue, but I need to break out after that. So done equals false, done equals true, if done break. So at that point, we're finished. And one of the problems that we have here is, again, we've got this offset by 1 situation, which causes a little bit of consternation here. So what I'm going to do instead is I'm going to do it like this. And then in here, I'm going to just do a modification of if work first sample point index equals 0, work first sample point index equals 1. So we'll still give them out in evenly arranged tranches like that, but we'll try to keep them aligned that way. So the problem here is we can do that, and I think that's probably the right way to do it. I'm also going to put this at the end. We also would have to go and actually cache line align all the rest of our stuff too, because we don't actually cache line or keep those cache lines aligned in the first place. So in other words, the various arrays that we're working with aren't necessarily cache line aligned at their start. So it doesn't really help too much to cache line align them there. I just wanted to make sure that routine was not adding insult to injury. I'm curious now what would happen if we ran with a lower number of rays as well. So we can basically get a full 16 frames a second by using the original solution now. 60 frames a second rather, I think we could do. Whereas before we weren't able to, right? So we're definitely getting closer. We're just on the edge of good, right? We're just on the edge of good. And we have a lot of options here. We just need to now quite cross over the finish line because we're getting pretty close, right? And we can run this thing multi-threaded now, which is nice as well, and see what the faster version of it would look like. We also could speed up some of this stuff quite a bit. Like we could do a lot better, and all of these routines are kind of garbage, right? They could all be sped up. So we know that we've got a lot of headroom to work with there. The question is just going to be, all right, look, what's the best path to really finish this up? Do we go GPU with it? Do we leave it on the CPU side? How do we tighten up that variance there? Because we're getting closer, but it's like we're still maybe wasting our samples or placing them improperly. So can we improve our stratified sampling? Can we improve the way that we're blending them together by being more conscientious about using those samples intelligently? So we still got a little bit to go. It's definitely getting there, but we still got a little bit to go. I'll go to a brief Q&A here. Looks like I got to do it in the other one. Can we temporarily turn off, turn down the frame to frame color interpolation to see how much increased sampling count stabilizes the solution? Yes, we can. Update. So this turns it off. Completely, right? And where's our ray count? So this was the original solution, 16 rays per sample point. And here was the increased ray number, which is 64. And it does do a pretty good job of reducing that flicker, but you can see that the flicker still remains, right? We also don't know which of these two is better for that, right? We haven't played with that too much. So here's just completely random. You can see that complete random sampling just does a better job, right? So we still have a lot of work to do there. And we can look at entropy counter here as well. So if we up the entropy frame count to a really high number, for example, now we get a lot more variance as things cycle through. You can see a lot more difference in the frames. So I don't know. Like I said, we still have a ways to go before we could really say that we've gotten this under control. But certainly we have a lot of ways to make it pretty good already, right? You know, if we jack the smoothing up, you pretty much get a completely usable solution here. It's just a little laggy, right? The flicker is pretty usable here, which is, I guess, what, like 50 frames of lag? So less than a second at 60 frames a second of lag. On the global illumination lighting would give us what I would consider a usable amount of flicker. Above that, we start to be bad. So at 20 frames, you can see the flicker pretty well, right? Again, not necessarily unusable in a nighttime game because the light sources are going to be flickery. So we could almost excuse that with fiction. So I'm not too worried about it either way. It's just, you know, I want to work on it and make sure it's good before excusing something with fiction, right? So yeah, and unfortunately the CPU version, because we're not optimized on CPU, isn't really that fast at the moment. So we can't try things like 256 lighting samples because it'd just be too slow. You wouldn't see the flicker anyway, really, right? Because the frame update is not fast enough, right, at that point, to really gauge whether the lighting looks visually okay once you get up to that number, right? Because it's just, we don't have an acceptable frame rate, so you can't really tell, is the lighting going to be acceptable at that frame rate or not. So anyway, that's where we're at. Can someone explain why to store and pass around one past last sample point index instead of calculating it at the loop part? Yes, I can. So the reason is because, well, let's put it this way. You could do it either way. If you wanted to, inside here you could add the number that was the fixed number you wanted to do, and then clamp it to the point count there. The reason that I don't tend to do that is because since it's going to have to be computed either way, I'd rather just pass it in as part of the work unit, because then the work units can be divided up however they want here, and it's clear to me what I'm sending out as a job to do. So if I wanted to make some jobs smaller than other jobs for some reason, I don't know why, but like, let's say in the future we want more sampling for some points than others, I don't know, I can just adjust how I'm doing it there. So I tend to always build my tiles for work and record the tile in the work unit rather than recomputing the tile later, just because it's usually free to do so, and it allows it to be more clear in the code what you're giving out in terms of work tranches. It just localizes the code to the part you want to. But you could have done it. All you would need to do is pass the first one, right? And more specifically, you wouldn't even have to do that. You could have just passed a work index, right? So, for example, one way to write this, and we chose not to do it this way because work queues are a little bit more flexible because you can put arbitrary jobs in there, right? So the arbitrary jobs that you could put in here can have any data you want, and that's valuable. But another way to write this is to just have a work number. So instead of a queue, you just get a work number and you look at what the work number is and you generate your work from that. And that's a more specific type of queue. Things have to have some hard-coded globals in there to understand what they're working with. But that's it, right? And that's a totally valid way to distribute work. And we could have done it that way. You just roll this code into the stuff that's up there that would automatically know how to take a work index out and generate what the range was from it. I just find it's a little cleaner to do it this way and more flexible. But if you really want to get it down to the nitty-gritty and not do any extra work that you don't have to outside, you could roll it down to just one number, and instead of a queue, you just have an incrementer. And it's very efficient. We don't need that efficiency because we have large work units, so the overhead is not much. But when that overhead gets more substantial relative to the work amount, it's not nothing. Valbus, why are we not using atomics when we modify data on the multi-thread pass? Because we're never touching the same data by more than one thread, that's all. The threads are just separate. If we wanted to reinstate these statistics, we still probably wouldn't use atomics here. We'd sum these up per thread and then use a single atomic at the end when the thread work exits right here to add them back in so that the cache line wouldn't bounce around. Given the restricted number of rays, should they be biased towards directions which are interesting to us, i.e. not vertically? Just wondering, are we interested in the light values gained from the ceiling compared to that from surfaces which the player can visually see on the screen? It's really hard to say, right? In one sense, you're right, because walls and such are only visible to us if they're around the periphery, and that makes good sense. However, you have to remember that there's things on top of things in the game world. So for example, lights like projectiles that are maybe bright and glowing will be flying directly over surfaces that need to pick them up. And so what I would say is I don't know that we can really say much about the general bias other than we want to bias for directions where the lighting contribution is reasonable. And since the cosine fall off means that really sharp angles just don't add very much, it kind of tends to be more towards the upward cone. Dr. Zul, can the raycast be optimized more? Yes, the raycast can be optimized dramatically more. For starters, we haven't even done simple stuff like look at the code to see if there's basic optimizations that need to be done. But beyond that, we could SIMD them so that we try to cast 4 rays at a time, for example, in certain circumstances, and other things like that could be made much more efficient. So yes, there's no question that we are inefficient right now in terms of raycast and could be much more efficient. Would increasing the size of the sample table make sense if we're going to 64 rays? Probably not. I mean, we don't want to stratify too much. So probably what I've got now makes some sense. I don't even know if that's a good stratification. So we may want something less stratified than that even. It may be that the sampling should really just be more into like 4 quadrants or something and biased slightly upwards, you know. Since you only use cubes, depending on the height of the light, you may know exactly where to cast since there can be, say, only 4x4 square over you at a certain height. I think it could work even if the light is placed as a wall. The generated table based on height would be flipped toward the normal. I don't think I follow that logic. I may just not understand what you're saying, though. Aqua XV, less technical question. How are you today? I'm all right. How are you? Yeah, I still just don't understand. I still just don't understand the question about the cube's height. I mean, the thing to remember is there's no such thing as the height of the light, right? The entire world is a light source. It's global illumination, so there's not like a light. We don't raycast towards lights in a biased fashion right now. We could, but if we did that, then our scheme gets worse the more lights there are, and I don't super love that. Because I want like lights to be everywhere if we want. I don't really want a light-based scheme in that sense. But we could do some stuff to try and, you know, improve that. We could, for example, shoot from lights outward. More, in fact, putting in the bidirectional sampling will do that automatically, because then when you shoot from the light, you transfer light outward. But the problem with doing bidirectional is that bidirectional makes the threading harder, right? Because the nice part about not doing bidirectional is that not doing bidirectional means that you don't have to worry about multiple people writing into the accumulation buffer for the lighting results. Once you go bidirectional, you do, because now you don't know where you're writing into that array. Yes, you are the only person who's looping over a particular block of sample points and writing into them in that fashion. But now anybody might be reaching into that same array as part of a bidirectional transfer and putting it there. So the bidirectional stuff, the reason I haven't done it yet and the reason that I'm kind of not sure how to do it in a good way is because I feel like it breaks that sort of unidirectional thread advantage that maybe is more important for the runtime overall. Now that the threading is working well, how does it scale with more threads? We don't have, I don't know why we're doing it this way. We have 6 and 2, so we're basically 8 threads. I think that's just how we decided to do it. So we don't really scale to any more than 6 threads at the moment. We just never launch more than that. So you can actually see that visually in a sense, because you can see that we have room on some of our threads that we're not really using there. And I think that's because we don't try to use all 8 for high priority processing like that. Now we could try to do that. I don't really know that there's any point to this, but you know, you could say, all right, let's say there's 8 high priority throughs. And again, we could go through and say, let's look at how many CPUs there are and base it off of that. But you can see here, if I go ahead and increase the number of high priority threads, then these all peg higher than they used to, right? So now we're really sucking up pretty much all of the CPU's processing time that's available on the machine for doing our lighting, and there's a little bit that's not used, and that's because, again, the lighting is not all of the time. So when we finish doing compute light propagation, we then drop into these other routines that still need to happen, which account for, you know, 5% of the time or something like this, and those are not multi-threaded. They're single-threaded, so they don't take the time. And so when you then take a look at how much time is being spent in here, you can see that there is a 5% gap or so up at the top, and that is expected because we are just simply not utilizing that time. And that's, again, why you also see that this number never creeps above 95%. It stays between 90 and 95% because we know that by default, 5% of our processing time is not multi-threaded anyway and never is going to be. So we know that there is sort of an upper limit there that we're never going to hit. But that's fine. That's not an appreciable amount of frames anyway. So you can see the difference in speed there. Here we're running at about 95 milliseconds. Well, let me launch it fresh so we have the exact same situation to look at. So here you can see at this frame rate, it's doing what, 53, 54. I don't think it's going to change that much if we knock it down to the lesser threads that we were using before. If I run it now, you can see it's more or less the same. It's a little bit higher, maybe, arguably gets up more towards 60 there. But it's pretty much similar. And the reason for that, again, is just because, you know, remember, there are not 8 processors in this machine. There's only 4. These are hyperthreads. So the degree to which we get more performance is only if we're waiting on reservation stations. Well, they're not called reservation stations anymore. Ports. It's only if we're waiting on ports, execution ports, or memory, right? And so we don't scale perfectly with more threads in terms of the amount of time we take to display. So, you know, we add 2 more threads and we only go up 6% CPU utilization, right? Whereas if it was perfect, right, we would expect to say 100 divide. If it were actually 8 cores that were totally independent, we'd expect to go up by 12% utilization for every one we added. And so if we add 2, we expect to go by 25. But actually, we only go up by like 7. So you can see that we're not getting that kind of. That's not the kind of utilization we're really getting. And you can see that just from this graph. I mean, this graph is more or less getting sort of close to pegging there. And you can see that these 2 are still working, right? So, you know. Anyway, I'm pretty sure that's how that's going. I don't know. Maybe I don't remember how this is working, and that's not really how that works, but I'm pretty sure that's how that works. And off you go. What's the status of using LLVM? LLVM is not something we're using on this, or even planning to use on this stream. We just are sticking with VC till we're basically done. I don't really like to switch compilers in the middle of a process if I can avoid it, unless I have to. How's the light source stored? The light sources are not stored as light sources or not. Basically what happens is every surface in the game has emission. So if the emission value is greater than 0 on a surface, then it emits light. That's all there is to it. No more wrist supports. Yeah, I don't use them anymore. Oh, use the new calculator. I'm sorry, Nixie. Yes, I'm sorry. I always forget about it. I'm not used to it. I'm supposed to be using this thing. I'm supposed to be doing this. Oops. Can you get an old answer? No. It'd be cool if you could get an old answer. Like if I had written this, I would put a number besides each of these that you could then refer to. You know what I'm saying to you? I don't know. Anyway, you know what I mean. Are there any ways to make it clear in your profiler that you are having these cache issues concerning threads and shared memory, or is this just something you have to look for a trial and error experience? Well, so yes. So in our profiler, I don't know that we could. Right? I don't think there's any way, unless I'm mistaken, that we could make that determination. However, if you have access to like VTune, the VXDs that allow you to read the performance counters in the CPU and stuff, which I don't know what the status is on these days. It's been a long time since I tried to write any profiling code that did like fancy CPU stuff. Inside the CPU, there are performance counters you can set which can recover information for you that have to do with stuff like how often you miss the cache and things like this. Now, whether that could ever tell you exactly this, that the problem is that you're ping-ponging a cache line back and forth, does it say that exactly? I don't remember what the performance counters are that you have access to. So, yeah, maybe yes, maybe no. But what I can tell you for sure is yes, you can get more information than this. You could at least see information about cache misses and how much you're stalling on them. And that might give you a hint, right? Now, whether you can actually get a number that really bullseyes the fact that you're getting in a ping-pong situation where it's not that you're reading in that much memory, but that you're actually just fighting over the same line, that I couldn't tell you. There might be performance counters that would help with that. There might not be. I don't know. So part of it's going to have to probably be experience. How much it can help you with that, I'm not sure. View history. So you can insert, yeah, I guess that's kind of good. I mean, it's not what I want. I want to be able to just get it while I'm in here, but I guess going over here and clicking is okay. I mean, it's better than nothing. That's probably a good thing, though. All right. Time to shut down. All right, thank you everyone for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. I feel like, to a certain degree, the variance is getting good. Like, we're getting pretty good here. We can improve what we've got quite a bit still, I think. So I don't think we've topped out by any means, but we've definitely learned a bunch, and I feel like we're making good progress all the time. I think the major decision we have to make is, do we want to move this to the GPU or not? And I don't know the answer to that question. It's a pretty difficult question. Obviously, when you move something to the GPU, you get a lot of bonus in terms of good job distribution and very wide floating point that happens automatically for you, and that's pretty good. But you do have a problem, which is that your memory accesses are much more likely to be stalls than they are in the CPU case, because the CPU has much better caching and random access memory. So for something like this, where we're talking about ray traversal, sometimes the GPU gets a lot less speed up than you would have gotten in situations where you weren't doing things like reading out a spatial hierarchy like that. So I don't really know what to expect if we move this to the GPU or not, and that's why it's a pretty hard decision to make. So we're going to have to make that decision, and I'm not sure exactly how, but that's just how that goes sometimes, so we'll have to cross that bridge trepidatiously. I don't know. And then the other thing we have to do, I think, at this point is just now really start to coalesce things together and make sure that we are doing the best we can in each of the situations that we've got. Improve that sampling, improve our blending, and just, get the variance down to the lowest possible thing we can with the tech that we've got, right? Yes, it does look good right now. No, it's not quite fast enough. We could optimize it more. And maybe we can, again, reduce the variance using a little bit more intelligence than we're using right now. I don't know. So that's really, again, still what we're doing, is just trying to turn that crank a little bit and make sure that we've gotten it to a pretty good place. But I don't know, I'm pretty pleased with the results, and it looks pretty cool, so I'm thinking it's pretty handy. Anyway, that's it for today. We'll be back next weekend with more coding. If you want to follow along at home, you can always pre-order the game at handmadehero.org, and it comes with the source code, so if you want to try your hand at making some good lighting routines, you could go ahead and do that, and let us know how you do. We'll be back here next week. Until then, have fun programming, and we'll see y'all on the internet. Take it easy, everybody.